So basically what I'm going to talk today is two main things. One is a brief introduction of what it means to do machine learning on data streams, and the second one is an introduction of the framework that we have for this purpose. So just to have the same common ground for everybody on what I'm going to be talking about today, we have just the topic of machine learning, which most of the people are familiar now. So this is a subfield of artificial intelligence, and what we're going to do is automatically find patterns in the data. What are the assumptions is that machines can learn from patterns and that they can make predictions. And this is with the minimal interaction of humans. So what is the goal that we have in machine learning is basically that we are going to use the data to build mathematical models that can give us or a description of the nature of that data. So taking that into account, we have the standard machine learning. This is, I mean, most people are familiar with this approach. It's based on batches of data. That's also known as batch learning, and this is the state of the art for many problems. So this is already very good starting point where we are taking off. And this is the basic pipeline for machine learning on batches. So basically, we have data that we are storing somewhere. Either we have it physically stored or we have it in memory, and then we're going to take that data to train the models, and once we have the mathematical models, we are going to apply to the data to have some predictions. That's the standard way to do it. But what are the challenges of this? Actually, the thing is that machine learning is not new. It's been around for a lot of time. It's a very well-established field with a very strong theoretical and technical and theoretical background. And now with the phenomenon of big data, we see that there has been reinvigorated this field. So now we have all these people working on machine learning. And what is the active field now is that we want to do machine learning at the scale. Basically, we want to take more data as it becomes available, and we want to keep pace with the data. So one of the things is that as we are generating more data and we are generating it faster, we are going to talk here today about two factors. One is volume, and the other one is speed. So for one example is e-commerce fraud detection. So basically here we have millions of operations daily happening, and what we want to do is that we want to detect fraud fast and correctly. The thing is that financial systems evolve, and they are always changing. So we need to keep pace with that context. And the other thing is that storing the data in this scenario is really not feasible. Really, like data that was maybe for some last year is not really useful anymore. And the thing is that if we are going to be losing training time, we may be losing also opportunities to detect some frauds. So this is very important, and this is like very key element that we don't have time to lose. So what is the alternative is that we can use data streams. And data streams, the most important thing is that we are assuming that data is infinite. So it's continuously coming, and what we're going to do is that we are going to maintain models in an online fashion. So what we're going to be doing is that we are going to incorporate data on the fly. We are unbounded on the training data. Basically, we don't have a train set. You just have a stream, an infinite stream. But given that this is unbounded, we have to be very efficient resource-wise. And the other thing is that, as I was mentioning before, the data streams change. So we need to be able to adapt to those changes. And finally, because we are adapting, we are going to have dynamic models. So what are the requirements when we are talking about data streams? Basically, we go down to these four requirements. One is that we are going to process one sample at a time, and once we do it, it's gone, because we are not going to keep anything. So we take one sample, we include it into the model, and then we let it go, because more data will be coming. Now, I mentioned that we are bounded to these two resources, memory and time, so we have a limited amount of memory, and we cannot work we cannot invest a lot of time onto training. We want to get the predictions as fast as possible. The final requirement is that we always want to be ready to predict. Why? Because since our data stream is infinite, we're never going to finish training. There is no, like in batch, that you have training and then prediction. No. Here we have a model that is always ready to predict at any point in time. So what it looks like, the pipeline for data stream, for machine learning on data streams, it looks a little bit like this. So basically, you have a stream of data that is infinite. You have a model at the bottom that is always ready. So what it's going to do is that it's going to ask the stream for data. And we either have two options. You get labeled data, in the case of supervised learning. And if it's labeled data, we're going to use it to train. And then we get back to the ready state. If we get unlabeled data, what is going to happen is that we are going to provide predictions, or the model is going to provide predictions, and then goes back to the ready state. So this is a little bit different to what we've seen in the batch learning approach. And this is, like I said before, this is a continuous process. It's always happening in this fashion. There is no end to it. So why this is important? It's because basically we are investing. We have an investment in terms of data size, where we are going to reach some limits, basically in batch learning. What is happening now is that as problems get larger and data sets get larger, we have to invest more resources. Namely, it's going to be time, memory, and this is going to imply also a cost. Because as data sets are getting bigger, we are going to new platforms or new services where we are going to get these resources. That at some point, we are going to reach a point where it's really unfeasible. Because maybe our problem is scaling too fast, but our budget is not scaling as fast as that one. So on the other side, what we are going to do with the stream learning is that we are going to have these resources in control. So what we are going to do is that this investment, this reasonable investment line is never going to be reached. So we want to keep it stable. That is the goal. So what are the upper limits in terms of resources? First, in memory, we want to be in control as data size grows. So basically, this is an infinite stream. So what we don't want to do is that we don't want the model to keep growing, because eventually we will run out of memory. On the other side, the upper limit for time is we want to have some sublinear time, because, as I said before, if we invest too much time into learning, what is going to happen is that we are going to start missing data, because the stream is continuously coming. So if we spend too much time into training, what is going to be happening is that we are going to start missing samples, and then our model is going to be basically obsolete. So this is a little bit of what it looks like when you compare batch learners and stream learners. In this example, this data set in specific contains 3 drifts. What we mean when we say drifts is basically a change in the concept. How this could happen is, for example, if your data is evolving, like I said before, in financial data that is changing, and then what happens in the batch setting is that basically you have a model that is being used in a different data. It was trained in some data set, and now it's being used in a different one. So as you can see, in this case, we are just trying to compensate, or the batch learner is trying to give some predictions, but it's really not happening. Like at the first drift, it just goes down, it just doesn't know what's going on. On the other side, if you see at the stream learner, it goes down because there is a change, but then it adapts quickly. And this is a very challenging problem for batch methods. There are some techniques where you are basically what you are doing, or what we are all doing now, is that if we see a change or a drop in performance, what we are doing is that we are investing time to first monitor the model, and then second to launch new trainings, and we have to wait until the training is finished, and then it's like we have to test all the pipeline again, and this is like an example of what it will look, how it looks like if you compare with the stream learner. So in this part, I'm just going to talk briefly about how you do machine learning. And for this, I'm going to focus on supervised learning. I'm going to talk about classification. So one example in classification. I'm going to talk a little bit more about what this concept drift means and how we can take advantage of it. And finally, how we do evaluation of models or stream models. That is slightly different to how we do it in batch learning. So the first thing I want to talk about is classification. This is a very basic task, or very common tasks nowadays, that we basically have a training set where we have labeled data, we have some features, and we have some classes for those features, and then what is the goal is that we want to get new data that is unlabeled, and we just want to give the prediction. One example is, for example, in spam filters. And one of the main methods for doing this, or one very popular method, is decision trees. Maybe most people are familiar with how decision tree works, but in any case, it's just basically that you are splitting the feature space into different paths. For example, this is a tree for a problem where you are going to buy or not a car. So what you're going to do is that you're going to split first at the beginning from the best feature. So in this case is if I have road tested the car, or if I can do it or not. If not, then I'm going to reject. I'm not going to buy it. Next one is the manage, and the next one is the age. So basically, you have a recursive induction where you take all the data and then you build the tree. So this is a very good method, very popular method, but the problem again is that we need all the data to train the tree. So one solution that actually was based on this is called the very fast decision tree, or the Hoeffding tree. And this is based on the same idea that you can create a tree, but in this case, it's based on the assumption that you need only small sample sizes to choose the split decisions. So how is this happening is that at the beginning, you have just one node, and then you're going to wait until you have seen enough samples, and then you're going to split that node. So basically, you're going to take the first node, and you're going to convert it into a split node, and then you have two leaves nodes, you split the distributions, and then you start getting a real tree. And this goes on as we get more data, but the tricky part here is how you decide when you should do the split. And for that, you are going to use the Hoeffding one. That's the mathematical background, which is the base for these decision trees. And basically, this is going to help you to define the correct point where you want to do the split. Basically, it's going to look into the statistics, and it's going to say, OK, at this point, I am confident enough that the split can be done. And then you are going to be growing the tree. The nice thing about this is that we keep the low variance probability feature of decision trees, and you have low overfitting. Basically, what we have is we have mathematical theories that we are very close to the batch learner method. So this is a very nice solution that was based on the decision trees, and it was adapted to the streaming scenario. On the other hand, we have concept drift. What happens is that concept drift is basically that we have dynamic, non-stationary environments. So basically what is happening is that the data distribution is changing. So if we are going to allow data distributions to change, what we are going to do in respect to concept drift is that we are going to signal when we see a change. And why this is nice, actually, this is a problem that we are facing in data streams, but actually can be a very good asset, because the application of concept drift detectors is that we can detect changes in the performance of our models, and this is done automatically. So, for example, one of the most popular, first, this is some of the patterns that you can find when we are talking about concept drift. Basically, in the abrupt change, we change from one concept to the other, just in one instant. Next sample that is coming corresponds to a new concept, and then we are gone. In the incremental case, we have intermediate concepts during the transition. In the gradual drift, what we have is that we have two concepts, and they are changing during a period of time, and they are changing between each other, and then we select one of them. The recurring concept, this is more like seasonal concepts that they are recurring, they are coming again. This could be maybe some phenomenon that is related to environments, that we have the cycles, we have the seasons, and maybe something is like something happens in summer, and then we have something different happening in the winter, but then the next summer we're going to see something similar. So the interesting thing about this, or the challenging part, is that we don't want to identify outliers as change. Basically because outliers are noise in our data, so our data can get noise, but we don't want to say, okay, due to this noise, we have a change. So we have to be sure when we are talking about concept diff is that we are actually identifying correctly a change. And one of the popular methods for doing that is the ADWIN change detector, or adaptive windowing. This method, what it does is very broadly is just taking a window of data, and what it's going to be doing is that it's going to have two sub-windows, and it's going to keep the distribution of those windows similar. So it's going to be monitoring those two windows, and while the data, or while the data corresponds to the same distribution, those two windows are not going to change. What happens is that when you see a new distribution coming, one of the windows is going to change. And once that happens, it's going to signal, okay, there is a change in your data distribution. It's going to drop the first sub-window, and then it's going to create another sub-window. So always keeps two sub-windows. It's very efficient in terms of time and in terms of resources. And it has the theoretical guarantees that it's going to maintain these two sub-windows with the same distribution. And it's one of the most popular algorithms that is being used in data streams, basically to automatically monitor the performance of models. The other thing that I wanted to talk about here is about the evaluation. Because as I mentioned before, when you are doing the training and evaluation, it's a different, there are small differences when you consider the batch setting. So basically what happens is that the two most popular options that you have in streams is the holdout method. This is very similar to what we have in batch learning, where we are just going to take some data and we're going to separate it and we're going to use it as a test set. So basically we have the stream, we take some data out, we don't use that data for training, so our loss estimation is going to be unbiased, because basically you are just applying your model on data that the model has never seen before. The other approach, which is specific to stream learning, is the frequential evaluation. And then in this frequential evaluation, what we are doing is that we are taking a sample, and then we are going to do a test, and then we are going to do a train. Basically, what is happening is that we take a sample, we show it to the model, we get an estimation, and then we use the same sample to do the training. We have to keep this order, because if we train first and then we do the testing, then we are just cheating, because we are showing to the model what we want to know. But in this case, if we keep this order, what we are going to gain is that we can use all of the data samples to train our model. So this is a very popular approach, because basically you're using all the information. And in the end, the error estimation is very close to what you would have in the holdout evaluation. So for these kind of challenges, what we have seen so far is that, or when I started working on this, is that there was not an official framework to work on this. There were different tools, and then I was interested in working on Python, but there was nothing in Python for doing data streams. And so the idea came that we wanted to bring something, a framework that would help in this scenario. So for this, we talk about scikit-multiflow, and we were just aiming at this goal of open artificial intelligence. And what were our goals when we started thinking about this is, first, we wanted to aim for reproducibility, because this is something that's vital for the scientific process. So this is our first goal, that we want to have reproducibility. We want to have faster development, basically because we want the users to be able to code or to use these tools, and they just focus in their own work, and they don't have to work or focus on the details. because there is so much things that are happening so fast, and it's like you don't have enough time to really go into details. And we wanted to bring the users closer to all these techniques. And we also wanted to foster collaboration, basically having a common framework so people can really work on this and share ideas and share issues and then work together on this topic. This is related to the democratization of machine learning, basically because we also want to bring this kind of techniques, this research field, closer to people that are not really familiar with it. And finally, we also are interested in maintainability, because what we found so far, I'm talking more about in the research part, is that many times you have some code that is working, but nobody else, or some people or some group of people were working on that code, and then it stopped, and then nobody knows anymore how it was working, or how you can use it or not. And then we said, like, we have to really get out of this cycle and move it into something that is going to be maintained not just by one specific group of people, but by a community. So thinking about those things is that we came up with this framework that we're calling scikit-multiflow, which is a multi-output learning and stream learning framework. This is being developed currently by TELECOM PARISTECH and École Polytechnique in Paris. This was inspired in two popular frameworks in Java, which are MOA and Meca. MOA is for stream learning, and Meca is for multi-output learning. And the thing is that we wanted to follow, or we wanted to give people something that was familiar for them. So in this case, we are following the scikit philosophy. So what we are aiming is that people who are familiar with scikit-learn should find scikit-multiflow familiar in the sense of how it works. And the nice things about this is that it's easy to extend, and it's easy to design and run experiments, basically allowing people to use these tools, test, and do their own experiments, and also extend their own methods, and basically get involved into the data stream mining. Another nice thing is that it works with Jupyter notebooks, which are very popular nowadays in data science. So we just wanted to bring this topic into the data science world. So for this, we had this at the initial release some months ago. It has changed now. We have added some minor releases from this time. What we were doing at this moment is classification and regression task. We have some concept drift detectors available. We have those data generators, the evaluators that I mentioned before. In this list, I'm just showing some of the methods that Meca and scikit-learn have. They have many other methods, but I'm just here showing the ones that are incremental. And the important thing here to show is that now you can see that scikit-multiflow is providing all these tools under the same framework. So if you are interested in trying these different techniques, you don't have to be just going around like trying different frameworks and trying to find a common ground and just making sure that everything works together. In this case, scikit-multiflow is the platform where you can find all these methods and compare them and just basically experiment with them. So for an overview of how is the architecture of scikit-multiflow, we have mainly three main elements. The first one is the stream class. Basically, we are going to take some data and we are going to convert it into stream. We're going to simulate the stream. So far, we have generators. Basically, we don't want to store a lot of data for doing tests. You can have some generators, and then basically you just generate data on the go. Other option is if you do have some data that is stored somewhere and you just want to try this, you can convert it into stream. And finally, you can use raw data. Basically, if you do some transformation of your data and then you want to test, you can also convert this into stream and use it. The second class would be the model class. This is basically, we have classification and regression models. Some are for single output, and some of them support multi-output. And also, as mentioned, we have some drift detection methods. These are not really models per se, but they are used in a lot of the state-of-the-art techniques. So we are integrating them with the models. And finally, we have the evaluator. And the evaluators, so far we have holdout and prequential. And basically is that we want to have this chance for the user to just set up an experiment, use the evaluator, and also just visualize what is happening. So basically, if you put all this together, you will have the platform where people just can experiment and just can play around and just come up very quickly with an experiment and start working on data streams from the beginning. So I'm just going to show a small demo of how it looks like. Of course, I got disconnected, so let's see if it works. If not, I'm going to launch it again. And in the meantime, what I can show you is how this version that is just basically one time that I run the notebook. In any case, what you can see here is basically I'm just importing some information, some of the methods that I'm using in this demo. Basically, just these methods are for some scikit-multiflow, for handling the data, generators, evaluators, etc. So basically here, for example, what I'm going to do is use a generator. So here I'm just using the C generator. It's a famous data set in the stream setting. And just basically, I'm going to say I'm going to use this function. I set some random state. This is very basic or familiar for people who are familiar with scikit-learn. I'm going to prepare the stream, so it's going to be ready. In this case, I'm going to use a support vector machine with SGD training. For this, what I'm actually doing is that I'm using a scikit-learn model, which is incremental, just to show up that we can interact with scikit-learn. So scikit-learn has some incremental methods, but not all of them support this. But we have this integration. And basically here what I'm showing is that we can do this. Here I'm setting the evaluation, the sequential evaluation, just for 20,000 samples, just to show that this generator is going to be giving me samples on the go, and it's going to stop until 20,000. Oh, yeah, let's. So how do I do that I use Linux, so I need some help. Control plus. Nope. Command plus. Yeah. Much better? Okay. Yeah, so here I'm just setting the evaluation, and this is basically my setup so 4 lines to set up my experiment. And then I'm just asking here to run the experiment, here in the evaluate. Let's see if this is running. Okay, cool. So it was command plus, right? Yeah. So I set up the stream, prepare it for use, set up my classifier. My evaluation is going to be sequential, and I'm just going to run it. And then as you can see, you start to see that some results. The nice thing is that, as I was saying before, you get predictions from the beginning. So you don't have to wait until some given time. You start from the beginning, you get some results. Sorry about that. And then when it finishes, it reports some information. About the training here, I use the accuracy and kappa. We have other metrics, but you can also see, for example, that we are measuring the memory. So here, memory is very small, 3 kilobytes is our model. This is a toy sample, but you get the idea. So another thing that I wanted to show is, for example, how do you do concept drift detection. So I'm just going to load this data set. It's a small data set that basically has two distributions. In the first half, it's a uniform distribution of 0 and 1. And the second half is a distribution of 0 to 7. As you can see here, the two distributions. And basically, I'm just going to create the ADWIN object. And I'm just going to feed ADWIN. And I'm just going to print wherever I think I found a drift. So in this case, the first time it thinks that it detected a drift was in around the 1,000 sample, which is good because the drift is in the 999 index. So from this, just another example. In this case, what I'm going to do is I'm going to load a file, and I'm going to use that data from the file. Again, I'm going to prepare. In this case, I'm going to use two classifiers. So one is the Hoeffding tree I talked about before, and another one is one that is called Hoeffding adaptive tree. And the nice thing about this Hoeffding adaptive tree, here I'm just setting up again, and I'm running it. The nice thing about the Hoeffding adaptive tree is that it uses ADWIN internally to detect changes. So this is an example where you also have a drift. And as you can see, both go below. The nice thing is that Hoeffding adaptive trees, in this uses ADWIN, it's aware of concept change. And what it does is that actually it changes its internal state. So the thing is that it keeps performance optimal, but also the memory, because it's changing internally. So when we finish, and we see the size of the models, you see that the Hoeffding adaptive tree is much more smaller than the Hoeffding tree. Both support working on concept drift, but one is handling it in a better way because it's aware of concept drift. But you can see now that I run the same, it's just a small experiment. I use a toy data set where it's the same that I showed before, having three drifts. One is here in the 5,000, one is in the 10,000, and one is in the 15,000 samples mark. And basically just showing that, for example, the Hoeffding tree is around 72%. The Hoeffding adaptive tree is a little bit more in terms of the mean. Performance, around 76%. And then these are the kind of things that you can do with scikit-multiflow. And the idea is that you can do this in very few lines of code. For people who are familiar with scikit-learn, I think you will find it familiar. We are taking some of the philosophy behind this. For example, we have also the fit function, but basically we are using the partial fit function, which is saying partially train the model on new data. The idea is that people can go and can extend this in an easy way. So if you are familiar with working with scikit-learn, I think that you can also find easy to work on scikit-multiflow. Okay, so that was for the demo part. So this is just to show how is scikit-multiflow doing on the wild. As I said before, we had just released this a few months ago. We are starting to do some trying to give more basis to the project in terms of an open source project. So basically now we are supporting different platforms. We have Linux, Windows, and Mac OS. We have different distribution systems, basically Python package index, GitHub, Dockers, and I can imagine that you are guessing where this is going to be next published, which is hopefully in next week. It should be in Anaconda. And just for terms of the project itself, we are using continuous integration and coverage just to try to keep the best practices for software development. We have so far identified some of the countries where this is being used. We are here just showing the information from pip, from the package index. I don't have information from Docker or from GitHub, but it's nice to see that people around the world are starting to using it. And we wanted to take this opportunity to be here to show this to you. So hopefully this will help reach other people that may be interested in this topic. And for that, we are welcoming people to contribute to the project. We are an open source project. As I mentioned, we are in GitHub. We have a pool of projects in different topics, namely classification, regression, clustering, and anomaly detection, but we are open to other projects or ideas. So if you are interested, please let me know or reach us through GitHub, and we will be very happy to work with other people. It was mentioned this morning in the keynote that the open source community or the open source movement can help to speed up development, and I'm really, really in the idea, or I also agree on the idea that this is the way to go. So finally, the takeaways from this talk are two. The first one is that the stream learning is an alternative to standard batch learning, where data is continuously being generated and it's assumed infinite. Data is not stationary, so basically we have concept changes. And finally, that scikit-multiflow is an open source framework in Python for doing machine learning for data streams, which is easy to extend and is easy to design and run experiments. With that, I would like to say thank you, and if you have questions.